Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer them at the end and to follow up with any unanswered questions via email. As I think you know, these tech talks have been designed to provide straightforward insights into radio frequency components. We talk about the related technologies and certainly the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. Shaun is the author of 2 U.S. patents and numerous white papers and technical articles on passive microwave technologies. He's been with Quantic TRM since the late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yeah, thank you, Paul. So really what we're going to talk about today is Space 2.0, and we'll start by defining what Space 2.0 really is. And then we'll move into what does that mean for a component manufacturer like Quantic TRM. And once we understand really what those requirements are, how do we go ahead and address those additional concerns that a space flight component requires. We'll then wrap it up with a summary and go over some Quantic TRM differentiators.
Okay, well, thank you. And to get started, what exactly is Space 2.0?
Well, that's a good question. So Space 2.0, the way that we've defined Space 2.0 here really is it's a migration, if you will, of technology and really what's been required for parts for spacecraft. Historically, parts for spacecraft have been really dominated by what they say is the very small part with 5 pounds of paper being shipped along with it. And what the 5 pounds of paper really represented was all the testing and documentation that was required, really to ensure a top-notch product that was going to perform for a very long mission life, where we couldn't afford a failure. So there was a lot of screening involved, a lot of analysis involved for these sorts of components. And really at that time, the industry was in a position of, cost is almost not a question even, and that they're happy to pay for all this additional testing and data. As the industry is no longer really being dominated by these very expensive GEO military type satellites, the need for all of that data has now been relaxed. So with the market changing and the need for all that data no longer being needed, the current really big push now is for a lot of lower orbit and building constellations as opposed to single-use satellites. So what happens here now is that the cost to launch is dropped dramatically. The number of people who are going ahead and having these launches are less. There's more people now being launched. We're now launching in constellations, so that if we happen to lose functionality on 1 or 2 satellites in a constellation, it's not a showstopper. These constellations typically have a shorter mission life. So therefore, the opportunity to go through there with some lesser cost sort of solutions certainly becomes financially advantageous. And really, so that's really the main thrust of Space 2.0. They still want decent parts, but don't necessarily need all the testing that they've had in the past.
Okay, so maybe could you explain a little bit more about the impact that this all has on for component manufacturers?
Sure. So really, what this means here is that with the mitigation of risk shifting from a prove-it mentality, which is all of the data and all of the documentation behind it, and the shift now is, okay, if you have heritage, we'll trust now that a lot of those things that we used to ask to prove are okay from behind the scenes. And in that case, really placing a little more trust in the vendor that they're doing the right thing rather than going through there and paying for all the subjective evidence to say that yes, we are doing the right thing. That being said, what are really the critical things that a component manufacturer needs to look at in order to make sure that the part will function in a space environment? Space environment is still very hostile and very different than what it is for the same component operating on the Earth where there's an atmosphere around it. So the lack of atmosphere and the low gravity environment does still pose challenges. And there are things that we have to make sure that are still addressed as part of the design. This is really where I think where the heritage comes in as far as to how these sorts of things look at. So things specifically that are unique to a space environment. Operating in a vacuum, you have multi-passion concerns, you have material outgassing concerns, and sort of the next sort of layer behind there that helps dealing with the vacuum is typically you want to have these components vented to address both of the previous concerns, as well as you want to have something that's mechanically robust. The ride going to space can be kind of rough on the rocket, and depending where you are on the satellite, there can be some very high shock and vibration levels. So those sorts of things need to be addressed as well.
Well, maybe could you share a few more details about each of these, I guess, key concerns that you've listed here?
Sure. So they're really, I think, as we're going through there, one of the main things that we need to be concerned with still is multi-paction breakdown. Multi-paction, I'm not going to go into it here, but it is a failure mode that can cause devastating effects on a satellite. It is a unique environment. It is a unique failure that happens only in a vacuum environment. And it is a failure mode that really, there are quite a few peoples who are now just getting involved in space may or may not understand fully what the impact of this is. So therefore, relying on a company like Quantic TRM that has full knowledge of this failure mode, how to predict it, how to do the analysis to ensure that this failure mode doesn't happen is critical for a lot of component manufacturers. The thing to keep in mind about multi-paction is that it is a resident failure mode that happens only in a vacuum. But it can also happen at very low signal levels. Signal levels as low as, say, about 30 volts can cause a multi-paction failure, and it could be devastating to the operation of a satellite. There are ways to mitigate this. There are things that we do here at Quantic TRM to make sure that this failure mode does not happen. And these are things I think that are very important for any satellite integrator, whether they're going in a LEO orbit for a very low-cost satellite or not. I think multi-paction mitigation is something that really needs to be done. Now, whether or not you test for multi-paction is another whole other thing. The test typically is quite expensive. But if we can go through there and at least do the analysis to say that we've mitigated it, that's usually all that these lower Space 2.0 customers really are concerned with. The next item really is outgassing. Outgassing is something that, again, is really critical for spacecraft operations. What you don't want to have is have material collecting on the outside of the satellite as it goes through its orbit. And this actually can have really horrible consequences, especially if you have any optics on the satellite. So therefore, we want to make sure that we have materials and on our material selection to make sure that we don't have outgassing materials actually on the component. Again, this is something that Quantic TRM has quite a lot of experience with. We have alternate materials that do not outgas or meet the NASA outgassing requirements. So therefore, this is mitigated just through material selection and really through history. A lot of very good materials that we typically use in the RF industry do outgas, and we have to make sure that we have suitable replacements for those parts for spacecraft. The other part really is venting of the part. And this is really also something that really, I think a lot of people that work in the terrestrial world really don't think about very much, is that the fact that once a satellite hits orbit, any gas or any kind of venting that happens from internal components doesn't really drift away. It stays very close to the satellite. The satellite is the largest mass local to it, and therefore you end up with this cloud of gas that kind of surrounds the satellite. And again, that kind of cloud of gas can collect on the surface, and it can cause other problems, very much like an outgassing event. Therefore, we want to make sure then that all components are vented in a way, really, so that all of the gas that is trapped on the satellite at launch is fully dissipated by the time the satellite hits orbit. So planning for that and calculating exactly how large vent holes need to be so that that vent actually happens, again, is something that is pretty important for most applications, and something that we do here routinely at Quantic TRM. And really the last item is making sure that we have parts that are mechanically robust. Again, we're talking about relatively high vibration and shock levels as part of launch. And that is something that, with all of the work that we've done with all of our spacecraft work in the past, as well as all of our military type work on some very severe platforms, this sort of analysis is something that we do routinely, and something that we're actually quite good at. So this is something, again, that's very important. So really, these are the highlighted things that we need to look for Space 2.0. Make sure that we don't have a multi-paction problem, make sure the part outgasses, make sure venting is adequate, and make sure we have a mechanically robust part. That kind of ticks most of the boxes as far as to what you have for parts for spacecraft. And if you're looking for really kind of your biggest bang for your buck, if you check these 4 boxes, you will go a long way into making sure that what you have will be successful in your mission when flying on a spacecraft.
So when you check these 4 boxes, as you've said, what are some of the typical modifications then that, as a manufacturer, what might a typical component manufacturer have to do?
Yeah, sure. So really, again, this is really the way that we handle it here at TRM. And basically, we start with a standard component. For multi-paction mitigation, things that we look at there are the connector very often needs to be changed. There are 2 things here really that deal with the connector. The first off is the epoxy that is used to stick the center conductor. For most connectors, does not meet the outgassing requirements. So therefore, we need to go to a mechanically captivated connector. Also, the connector launch itself, the interface between the connector and the housing is usually a place where multi-paction can occur. So this is the first place where we go in and do the sort of modifications to make sure that we mitigate the multi-paction problem. And really, this very often goes into going with interlocking dielectrics in order to alleviate the opportunity for an air gap to happen, and have that vacuum area for that electron to jump across and cause the multi-paction failure. So really, this is one of the first places where we go in there to go in and actually have that modification, is to go in there and actually have this design change, really, where we can go in and have a change to the design where we can actually have the interlocking dielectrics to actually eliminate the possibility for multi-paction to happen. We also go through the rest of the circuit as well and go through all the other points that we have to go in there and mitigate that. Outgassing is a thing that is related to a specific material. And basically what it is that when you pull a vacuum on a particular material, how much of that material gets vented off. There are certain materials, certainly when you pull a vacuum on it, it loses more material than others. And really what we're looking for is a material that is stable when put into a vacuum. There are certain guidelines that NASA has built to have to things that are acceptable as far as part of what you have on a spacecraft. Venting is something really that I mentioned previously. That is an area really where you have to make sure that you can get all of the trapped air out of the component during the time that's going through launch. So going from sea level pressure up to a vacuum, for some rockets, this can happen in a matter of minutes. So we have to make sure that the vents are large enough, make sure that there's no trapped area anywhere in the assembly that can kind of hold the air in there and then slowly let it out later on. So you want to make sure that you have a good sized vent and enough of them actually to make sure that the entire volume of air that is inside the component can be released and dissipated while the satellite is still on its ascent, not have it continue to leak out gas once it's on orbit. And then again, the last piece there really is looking to make sure we have a mechanically robust design, making sure that we can survive the shock and vibration requirements.
Well, excellent information as usual. Can you summarize?
Sure. So basically, for Space 2.0, what we're looking at here really is the requirements are changing. You know, the days of the government coming in with very deep pockets, wanting to verify and test every parameter and every environment really are one of that areas really is it's becoming a bit of a overkill, or people just aren't willing to pay for all that data anymore. So as a result, really what we're looking at now is relying a lot on heritage of companies who have done all that testing and really understand what the risks are to be able to supply components that will then be successful on these programs. So what do you test for and what do you not test for, and what is important from a design standpoint? Again, a lot of the new space people are looking to people who have been building these military spacecraft components like Quantic TRM and saying, okay, what's important? What is the risk factor here? And really, where do we have to be careful so we don't have a failure on orbit? And really, the 4 items that I've been highlighting here in this talk, I think really are the ones that are really the most critical, most important for a component manufacturer. And again, they're multi-packaging mitigation, material selection to make sure that we meet the outgassing requirements, venting of components to make sure that we don't have a slow leak on orbit, and also making sure that we end up with a lightweight, robust mechanical designs, so we can go in there and have something that'll work very well once it makes it to orbit, and then operates optimally once it gets in orbit. As far as what we have for heritage, Quantic TRM has been in the space business since 1999. So we have decades of experience at this point, designing components just like this. And moving forward into the Space 2.0 era, we have some very good heritage drawn, which helps us be successful moving forward and actually educating our customers sometimes on what's really critical going forward for Space 2.0. And as part of that, we have Quantic TRM has designed hundreds of different components on various platforms. We have platforms on military satellites, commercial satellites, LEO orbit satellites, as well as deep space missions. So we have heritage on all of the above, and we like to bring that to our Space 2.0 customers going forward.
Okay. And beyond the heritage, which is you've spoken nicely about, what are some of the other Quantic TRM differentiators that you might talk about here?
Sure. So Quantic TRM is a custom manufacturing house. Now, custom manufacturing does not mean that we do not have commercial catalog sort of commercial type products. We have those as well. But really, what we like to do as part of the custom sort of work is we like to work with our customers. And by saying that, really, the thing there is we want to make sure that what the customer is asking for is really what the customer needs to support their project. And very often going through and discussing all of the parameters and trade-offs, we can make sure that the customer gets exactly what it is they need. It really comes down to making sure that we can select optimized materials, design approaches, packaging, and if testing is required for the program, to be able to supply that as well. Really, Quantic TRM, to sum it up, really is a solution provider that also provides hardware. So it's a great differentiator for us is to really our desire to want to work with our customers to make sure that they get exactly what it is that they need, and have the opportunity to actually discuss all the trade-offs that we have with our various with the various options that we have available to us, to make sure that really what the customer gets is really the best solution for their problem.
Okay, thank you. And I think we do have time for at least one question. And the first one is, it said, geez, you've given us some examples of the typical modifications for Space 2.0 products. Are there other modifications a custom manufacturer might need to make?
Yeah, absolutely. Like I said, the four that I highlighted here really are, kind of the big ones. There are other modifications, for example, that we may need to do, and that's part of this one-on-one discussion we like to have with our customers to make sure that we address all of those issues. Sometimes it is a matter of modifying a mounting configuration so that they can better mount it up into the next higher assembly. Sometimes it is some testing. Very often, there are some parameters that are critical. For example, whether it's amplitude tracking over temperature or phase tracking over temperature, and these sorts of parameters are something that they do cost a little bit more to go through and validate. But if these are really important parameters to the system, it's something that we're very happy to go through and make those measurements, and also design those sort of stability features into the product as we're doing the initial design.
Okay. Well, thank you, Shaun, and thanks again to everyone for joining us. If you are a customer and you have additional questions, please feel free to call the engineering hotline. We would love to hear from you. The number's on your screen, 888-677-6877. Of course, there's no cost for these conversations. If you're one of our field sales representatives, then you know your calls are always welcome, and you can contact us through the portal. And looking ahead in conclusion here, I think the bullets on the screen speak for themselves. And our next Tech Talk will be on Tuesday, November 28th, and the topic will be phase and amplitude balancing products. Thank you again, Shaun.
Yeah, thank you.